Welcome to the deep dive. Today we're diving into the world of quantum machine learning, or QML for short.
Yes.
Sounds pretty intense,
They're
right?
definitely not light reading.
Exactly. And you know what? That's exactly why we're here. We're going to break it down, make it understandable. We're going to unlock the secrets of how quantum computers could totally revolutionize how we learn from data. You sent us supervised learning with quantum computers, so that's going to be our focus.
Excellent choice.
I know, right? So before we kind of leap into the quantum realm, maybe let's start with the basics. Regular machine learning. What is that all about?
Well, think of it as teaching a computer to learn from data, sort of like we do.
Oh, okay, like recognizing faces or
Yeah,
something.
exactly. You feed it data, it finds patterns, and then it uses those patterns to make predictions about new data. It's all about finding patterns in data, just like we do, but with algorithms.
But how do you make sure it doesn't just memorize the data it's seen before? I remember that always being a challenge.
Ah, you're talking about overfitting. Like, imagine drawing a curve that perfectly fits a bunch of random dots. You could get this super complex, squiggly curve that hits every single dot, but it wouldn't actually capture the overall trend.
Oh, I see. So it's like cramming for a test. You might ace that one test, but you won't really understand the material,
That's
right?
a great analogy. In machine learning, we use what we call training and test sets.
Training and test sets.
Yeah, to make sure our models actually can generalize well to new data that they haven't seen before. It's like giving a student practice exams before the real deal.
Okay, that makes total sense. So we've got this foundation of traditional machine learning. Now, how does the whole quantum thing come into play?
Well, prepare yourself. We're about to enter the realm of quantum mechanics, where the rules are, let's just say, a little bit different.
Bring on the weirdness. I'm ready.
Instead of bits, which can be either a 0 or a 1, we have these things called qubits.
Qubits.
And these qubits can be in a superposition.
Superposition. Okay, that's that's starting to sound a little sci-fi, isn't it?
It kind of is. Imagine a coin spinning in the air. It's both heads and tails at the same time until it lands.
Okay, I think I'm getting it. So these qubits can be in multiple states at once.
Exactly. Until we measure them, they're in a combination of all possible states.
Whoa. So how do we actually use these magical qubits to actually do anything useful?
That's where quantum computers come in.
Quantum computers.
They're specifically designed to manipulate and control these qubits, allowing us to harness the power of superposition and other quantum phenomena to do calculations that would be basically impossible on a classical computer.
So they're not just faster computers. They're doing something completely different.
Exactly.
Okay, I'm hooked. Give me an example. What can they do that my trusty laptop just can't?
Imagine you have a maze, but this maze has like a million different paths, and you need to find the shortest one. A classical computer would have to try each path one at a time.
Oh my gosh, yeah, that would take forever.
Right. But a quantum computer, using something called quantum parallelism, could explore all those paths simultaneously.
Whoa, that's like having a million tiny explorers all searching at once. That's incredible. So
Yeah.
quantum computers can basically explore multiple possibilities at the same time.
Exactly. It's one of the key things that sets them apart from classical computers.
But how do we actually feed information into these quantum computers?
Yeah.
It's not like you can just type data into them.
Right. You can't just type it in. We need a way to translate our classical information into the language that these quantum computers understand.
Okay, so how do we do that?
Well, that's where quantum information encoding schemes come in. We use these schemes to represent classical data using qubits.
Encoding scheme.
Yeah, it's like translating a book from, I don't know, English to, let's say, Mandarin. You need a set of rules to convert the letters and words.
Okay, so we're translating our data into the language of qubits. Got it.
Mm.
But how do we actually get those qubits to do something useful with that data?
Well, that's where the magic of quantum machine learning algorithms comes in.
Quantum machine learning algorithms.
These algorithms are specifically designed to take advantage of those unique capabilities of quantum computers, like superposition and entanglement, to perform machine learning tasks in a whole new way.
Ooh, okay, so this is where things get really interesting. What kind of advantages can these quantum algorithms offer compared to, the classic algorithms that we're using today?
Well, for one, speed. Imagine crunching through a calculation that would normally take a classical computer years, maybe even centuries, and doing it in a matter of minutes or hours on a quantum computer.
Okay, that's a game changer.
It is.
What kind of impact could that have on, I don't know, drug discovery or material science?
Think about designing a life-saving drug or a revolutionary new material. If we could simulate those complex molecular interactions involved, but at lightning speed, we could accelerate the pace of discovery and innovation just dramatically.
Okay, that's mind-blowing.
Yeah.
But speed isn't the only advantage, right? What else can these quantum algorithms do?
Well, there's also the potential to learn from data that's inherently quantum mechanical in nature.
Quantum data.
Classical algorithms simply can't handle that kind of data.
Okay.
But quantum machine learning algorithms, well, they could potentially unlock insights that are hidden within that quantum realm.
It's like opening up a whole new dimension of data that we've never been able to access before.
Exactly. And there's the potential for increased robustness against noise, which is a major challenge in both classical and quantum computing. Some quantum algorithms have actually shown to be more resilient to errors and imperfections in the data,
Oh, wow.
which
Oh, wow.
could lead to more reliable predictions.
So we've got speed, access to this new kind of quantum data, and increased robustness. It sounds like quantum machine learning has the potential to be a total game changer.
It definitely has the potential.
But let's be real, there must be some challenges too, right?
Of course. Building and scaling quantum computers is incredibly difficult and expensive.
Okay.
We're still in the early stages of developing fault-tolerant quantum computers with a large number of qubits.
So the hardware is still a major hurdle.
Absolutely. And even developing efficient quantum algorithms is a complex and evolving area of research. It's not just about taking a classical algorithm and making it quantum, We need entirely new ways of thinking about computation and learning.
Right. Okay, so it's a whole new ball game. And then there's the whole challenge of like integrating these quantum computers into our existing classical computing infrastructure.
Exactly. We need to bridge the gap between those two worlds to make these powerful quantum tools actually accessible and practical.
Okay, so it sounds like a lot of moving parts, but the potential rewards, they seem enormous. So where do we start?
Let's start with supervised learning,
Supervised learning.
where we train a model on labeled data to make predictions about new, unseen data. It turns out quantum mechanics can offer some surprising tools for enhancing this type of learning.
Oh, okay. Like what? Give me an example.
Well, remember those linear models we talked about? The ones that
Uh-huh.
try to find a linear relationship between inputs and outputs?
Oh, yeah, like fitting a straight line to a bunch of data points.
Exactly. Turns out quantum computers could be incredibly good at performing those kinds of calculations.
Really? How so?
They can take advantage of superposition and entanglement to perform linear algebra operations, like much faster than classical computers.
So instead of fitting a straight line, we're fitting a quantum straight line.
Not exactly, but you get the idea. We're using quantum mechanics to enhance these models.
Okay, that's exciting. What other kinds of quantum algorithms are out there for supervised learning?
Well, there are kernel methods.
The kernel method.
Yeah, they're widely used in classical machine learning to classify data and make predictions. These methods rely on these functions called kernels, which measure the similarity between data points.
Oh, okay. So it's like figuring out how closely related different data points are to each other.
Exactly. And quantum computers might actually offer a completely new way of thinking about these kernel methods. By leveraging quantum state preparation, we could explore a much richer set of kernels.
Wow, it's like we're expanding the possibilities of kernel methods into like a whole new dimension.
You could say that.
What other quantum approaches are there?
There are probabilistic models where we can represent those classical probabilistic models, like Bayesian networks, using quantum states.
Bayesian networks, those are the ones that help us make decisions under uncertainty, right?
Exactly. And it turns out we can actually represent these networks using quantum states, opening up the possibility of performing Bayesian inference, but on a quantum computer.
So it's like taking these powerful tools and giving them a quantum upgrade.
Exactly.
This is incredible. But I'm
Yeah.
curious, how do we actually train these quantum machine learning models? Are there specific quantum techniques for that as well?
Absolutely. There's a whole area of research dedicated to developing quantum algorithms specifically for training these models.
Can you give me an example?
Sure, one approach is called quantum BLAS. It aims to accelerate the basic building blocks of linear algebra.
Oh, boss.
Yeah, it stands for Basic Linear Algebra Subprograms.
Okay.
And these are the fundamental operations that underpin a lot of machine learning algorithms.
So quantum blast is like a quantum-powered toolbox for linear algebra.
Exactly. By accelerating these fundamental operations, quantum loss could potentially speed up the training process for a wide range of models.
Okay, awesome. What other quantum training techniques are out there?
Another interesting approach is variational algorithms.
Variational algorithms.
Yeah, they involve optimizing a set of parameters in a quantum circuit to minimize what we call a cost function.
So it's like tweaking the knobs of a quantum circuit to find the best settings.
Exactly. The cost function, it's typically related to how well the model is performing. Variational algorithms they're particularly well suited for near-term quantum computers because they can be implemented with relatively simple circuits that are less prone to errors.
So we're adapting these algorithms to work with the limitations of the current hardware.
Exactly.
That's clever.
Yeah.
What are some of the ways that these quantum training techniques are actually being used today?
They're being explored for tasks like regression, classification, and even training quantum neural networks.
Quantum neural networks.
Yeah, it's a fascinating area of research that combines neural networks with quantum computation.
So it's like building a hybrid brain that combines both like biological and quantum systems?
You could say that,
Yeah.
but it's important to remember that quantum neural networks are still in their very early stages.
Right.
There's a lot we don't know about their capabilities.
It's cutting edge, it's the frontier.
Yeah.
But speaking of training, how do we actually evaluate the performance of these QML algorithms? Is it similar to how we evaluate the traditional machine learning algorithms?
That's a great question. Evaluating QML algorithms presents some unique challenges because of the probabilistic nature of quantum computation.
Probabilistic. You mean that the results of these quantum computations aren't always predictable?
Exactly. Remember those spinning coins we talked about?
Yeah.
Well, the outcome of measuring a qubit is probabilistic, just like the outcome of a coin flip.
Okay, so we can't always guarantee a specific outcome. So
Yep.
how do we deal with that when we're trying to figure out how well a QML algorithm is performing?
Well, one common approach is to run the algorithm multiple times and then average the results.
Okay.
It's like taking a poll to get a sense of public opinion.
Oh, I see. So we're using statistics to kind of account for the randomness of quantum mechanics.
Exactly.
Are there any other differences in how we evaluate QML algorithms?
Yes. One is the resource requirements of the quantum algorithm.
Resource requirements, you mean like the number of qubits needed?
Exactly. And the complexity of the quantum circuit. Quantum resources are still very limited, so it's important to consider how much computational power an algorithm needs.
Makes sense. It's a balancing act.
Exactly. Another important thing to consider is the potential for what we call quantum advantage.
Quantum advantage.
That's when a quantum algorithm can actually outperform any classical algorithm for a specific task. Demonstrating quantum advantage is a major goal in QML research.
Oh, okay. So it's like proving that a horse can run faster than a car.
Exactly.
Okay, so we need to be careful not to overhype the capabilities of these QML algorithms.
Absolutely. Rigorous evaluation is essential. But even with these challenges, the field of QML evaluation is rapidly developing.
That's good.
Researchers are creating new methods and benchmarks to assess the performance of these algorithms.
This is fascinating. It seems like every step we take into this world reveals like new complexities and possibilities. I'm ready to like explore the potential impact of QML on, I don't know, different industries and fields. What about you?
Me too. Let's dive in.
Okay, great.
So in supervised learning, we're basically giving the algorithm labeled examples and saying, hey, figure out the pattern here so you can predict the labels for new examples.
Right, like we're giving it instructions and showing it, how to do things. But with unsupervised learning, it's more like go figure it out on your own. That seems a lot harder.
It is, but it's also incredibly powerful because it lets us discover those hidden structures in data that we might not even know to look for.
It's like giving a detective a bunch of clues and saying, solve the case. What kinds of problems can we actually solve with unsupervised learning?
Well, one classic example is clustering.
Clustering.
Yeah, where we group similar data points together. Think about analyzing customer data for a retail company. An unsupervised learning algorithm could group customers based on their buying habits, right?
Yeah, that makes sense. So instead of like manually grouping customers, we're letting the algorithm kind of discover natural groupings on its own.
Exactly. And this can lead to more effective marketing, right?
Right.
Another important area is something called dimensionality reduction.
Dimensionality reduction.
Yeah, where we try to simplify complex data by reducing the number of variables.
Okay, so like High-dimensional data can be really hard to work with. So how does dimensionality reduction actually help with that?
Imagine trying to understand a data set with hundreds or even thousands of features. It'd be impossible to visualize all those dimensions at
Oh,
once.
yeah, totally.
Dimensionality reduction tries to find a lower dimensional representation, but it still keeps the most important information.
Okay. So we're kind of like compressing the data, but without losing too much detail.
Precisely. Now, how does quantum computing fit into all of this?
Well, quantum algorithms could offer some big advantages for certain unsupervised learning tasks.
I'm all ears.
One promising area is quantum clustering. Classical clustering algorithms sometimes struggle with high-dimensional data, and they can get stuck in local optima.
Local optima. What's that?
It's like imagine you're hiking and you think you've reached the highest peak, but there's actually an even higher one just hidden behind another hill.
Oh, okay. So you think you're at the top, but you're not really.
Exactly. Quantum algorithms leveraging principles like superposition and entanglement could potentially explore the solution space more efficiently.
So we're giving those algorithms a quantum boost,
Yeah.
helping them see the bigger picture, so to speak.
Exactly.
What about dimensionality reduction? Can quantum computers help with that as well?
They can. Quantum algorithms are actually being developed for techniques like principal component analysis or PCA.
Yeah, which aims to find the directions of greatest variance in the data.
Okay, so it's like finding the most important features of the data.
You could say that. And quantum algorithms could do PCA faster, more efficiently, especially for high-dimensional data.
This is incredible. It seems like quantum computers could totally revolutionize unsupervised learning, finding patterns that we could never find before.
It's an exciting area of research, and it has the potential to lead to some major breakthroughs.
But before we get too carried away, let's step back for a second and think about the bigger picture. Where are we actually at in terms of like the maturity of this field?
Well, QML is still it's still relatively young, but it's evolving quickly. But there are some challenges that we need to overcome.
Okay, like what kind of challenges?
Well, one of the biggest is the availability of really powerful and reliable quantum computers. We need quantum computers with more qubits, longer coherence times, and just better error correction.
So it's a hardware problem.
Yeah, to a large extent, yes. But we also need to develop more efficient algorithms.
So it's a software problem too.
It's both. It's a co-evolution of hardware and software.
Okay, so as quantum computers get better, we can develop more sophisticated algorithms. And as the algorithms get more efficient, we can push the limits of what we can do with those computers.
Exactly. It's a symbiotic relationship.
Cool. And what about the integration of quantum computers with, our existing computing infrastructure?
That's a crucial element as well. We need to find ways to seamlessly connect these quantum devices to our data centers and our current workflows.
Right. We can't just have these quantum computers off doing their own thing. We need to find ways to make them work with the systems we already have.
Exactly.
Okay, well, it's clear that QML is a field with just massive potential, but also with a lot of challenges still to overcome. What are some of the key areas of research that are like driving this field forward right now?
Well, one of the big ones is developing more efficient and robust quantum algorithms. We need algorithms that can handle real-world data with all its, noise and imperfections.
So it's about making these algorithms more like practical and usable for real problems, not just theoretical problems.
Exactly. Another key area is exploring new quantum hardware platforms and architectures. We're looking at things like trapped ions and photonic qubits.
So it's a search for the best possible quantum hardware for machine learning.
You could say that.
And we're also looking at, hybrid quantum classical approaches,
Exactly.
combining the strengths of both quantum and classical computing.
Right.
So it's not about seeing them as like competitors, but figuring out how they can work together.
Exactly. And another area that's really important is the theoretical foundations of QML. We're really trying to understand, why and how these quantum algorithms actually work so well.
So it's not just about building and testing algorithms, but
Mhm.
really understanding the science behind them.
Exactly. That deeper understanding is what's going to lead to those breakthroughs.
This is so cool. It seems like every new discovery just opens up like a million more questions and possibilities.
It does, and it's what makes this field so exciting.
It really does. I'm really excited to see where this all goes.
Me too. We're really just at the beginning.
Yeah. You mentioned earlier that QML could revolutionize drug discovery. Can you elaborate on that a little bit? Like, how are these algorithms actually being applied in this field?
One of the biggest challenges in drug discovery is understanding how molecules interact. And these interactions, they're governed by the laws of quantum mechanics.
So they're really complex.
They are, and classical computers, they struggle to simulate them accurately. But quantum computers are actually naturally suited for this task.
Oh, okay. So it's like using the right tool for the job.
Exactly. Quantum computers can simulate those molecular interactions much more efficiently and accurately.
That's amazing. So we can essentially use quantum computers to design drugs.
In a way, yes. We can simulate how a drug molecule might interact with a target protein, for example.
Wow. So it's like having a virtual lab where we can test millions of different drug candidates before even like making them in a lab.
Exactly.
This could completely change how we develop new drugs and treatments.
It could.
That's revolutionary. What other applications of QML in drug discovery are you excited about?
Well, QML could also help us analyze huge data sets of biological and chemical information to identify good drug targets.
Drug targets, what are those?
They're the specific molecules or pathways in the body that a drug is designed to interact with.
Oh, okay. So finding the right drug target is basically the first step to developing an effective treatment.
Exactly. And QML algorithms could help us sift through all that data, all those mountains of data, to pinpoint the most promising targets.
So it's like a quantum detective that can find the clues hidden in all that data.
Precisely. And QML could even be used to optimize the properties of drugs that we already have.
Optimize? Like how?
Well, we could use QML algorithms to adjust the structure of a drug molecule, improve its absorption, maybe reduce side effects, or even make it better able to cross the blood-brain barrier.
Wow, so it's like fine-tuning a drug's performance using quantum computation?
Exactly.
This is incredible.
Yeah.
It seems like QML has the potential to, like, completely transform drug discovery, personalized medicine, targeted therapies. It's amazing.
It's definitely a field with huge potential, but QML's impact goes way beyond medicine. What about material science?
Material science.
Yeah.
That's all about understanding and designing new materials, right?
Right. From the materials used in aircraft to the semiconductors in our electronics, material science is everywhere, and QML could revolutionize this field too.
Okay, I'm intrigued. How does QML apply to material science?
Well, one of the big challenges is predicting a material's properties based on its atomic structure. And this involves simulating those interactions between electrons and atoms, which are, you guessed it, governed by quantum mechanics.
So just like with drug discovery, classical computers have trouble simulating these quantum systems.
They do, but quantum computers, they're a natural fit.
Right.
They can simulate these systems much more efficiently and accurately. And this could change how we design new materials.
So instead of relying on trial and error, we could use quantum computers to like design materials from scratch, predicting their properties before we even make them.
Precisely. Imagine designing a material that's incredibly strong and light, or one that can conduct electricity with no resistance. QML could make those things possible.
That's mind-blowing. QML could lead to all sorts of breakthroughs in energy, transportation, electronics.
Exactly. And we're already seeing the early signs of that happening.
That's so cool. It seems like everywhere we look, there are new and exciting applications for QML. What other areas are you particularly interested in?
Well, one that I find fascinating is the use of QML in financial modeling.
Financial modeling.
Yeah.
Yeah.
Predicting market trends, assessing risk, making investment decisions.
Oh, right. That's a field that relies on tons of data and complex algorithms.
Exactly. And QML could revolutionize that by speeding up calculations, improving risk assessments, and maybe even uncovering those hidden patterns in market data.
So we could make smarter investment decisions, manage risks better, and maybe even predict market crashes.
Well, predicting market crashes perfectly, that's probably still a long way off.
Okay.
But QML could definitely help us understand those factors that influence the financial markets much better.
That's still super valuable. What specific types of financial modeling tasks are, like, well suited for QML?
One area is portfolio optimization.
Portfolio optimization.
Yeah, it's the process of choosing the best mix of assets to invest in.
Oh, okay, like stocks and bonds and all that.
Exactly, and it's a computationally challenging task.
Yeah.
But QML could potentially do this much more efficiently than classical algorithms.
So instead of just relying on like gut feelings or traditional methods, we could use quantum computers to make really smart investment strategies.
Exactly. And QML could also be used to improve risk management, identifying and mitigating potential risks.
Right, because in finance, there's always risk, right?
Always. Financial institutions face all kinds of risks, from market changes to credit defaults.
Yeah.
QML could help us model those risks more accurately and develop better strategies.
So we could use quantum computers to create a more stable financial system.
It's possible.
Wow.
But it's important to remember that QML is still early in its development. There's still a lot of work to do.
Right. But it's definitely a technology with the potential to like change how we think about finance and investment.
Absolutely.
And it's not just about making money either, right?
Right.
QML could also help us address some bigger societal issues.
Like poverty and inequality.
Really? How?
Well, it could be used to create more accurate and fair credit scoring models, for example.
Oh,
Or even to better allocate resources in social programs.
so it's not just about making financial markets more efficient, but also about making them more just and equitable.
Exactly. QML could be a really powerful tool for social good.
This is incredible. It sounds like QML could touch just about every aspect of our lives.
It has that potential, yes.
Okay, well, before we get lost in all the possibilities of the future, let's take a minute and think about what we've learned so far.
Okay.
We started by exploring, the basics of machine learning, both the traditional way and the quantum approach, and then we went into that mind-bending world of quantum mechanics.
Superposition, entanglement, quantum parallelism.
Yeah, all that fun stuff, and we saw how those concepts could actually be harnessed to create these powerful algorithms.
And we've looked at the potential of QML across so many different fields, from drug discovery to material science to financial modeling to social good.
Right. It's clear that QML has the potential to really revolutionize things, but it's also facing some pretty big challenges.
Yes, it is. We talked about needing better quantum computers, better algorithms, and better integration with classical computing systems.
Right. It's a huge undertaking, but the potential rewards seem worth it.
Yeah.
The future of QML is it's bright. I'm excited to see what happens in the next few years.
Me too. A very exciting time to be working in this field.
Well, before we completely lose ourselves in the possibilities of the future, let's bring things back down to earth for a minute. You mentioned earlier that QML could have a huge impact on drug discovery. Can you tell me a little bit more about how that would actually work? Like, how are these quantum algorithms actually being used in that field?
One of the key challenges in drug discovery is understanding those interactions between molecules.
Okay.
And these interactions, well, they're governed by quantum mechanics, which makes them incredibly complex.
Right.
Classical computers really struggle to simulate them accurately, but quantum computers, they can do this naturally.
Right, because they're quantum themselves. So we could basically use quantum computers to design drugs at the atomic level.
Yes, we can. We can simulate how a drug molecule interacts with a target protein in the body, for example.
Oh.
And this could help us predict whether a drug will be effective.
That's amazing. So it's like having a virtual lab where you can test out, millions of drug candidates without actually having to synthesize them in a real lab.
Exactly. It could really speed up the whole drug discovery process.
That's revolutionary. What other applications of QML are you excited about in the field of drug discovery?
Well, QML could also help us analyze those vast data sets of biological and chemical information.
Right, because there's so much data in biology and chemistry.
There is, and QML could help us find those promising drug targets.
Drug targets.
The specific molecules in the body that a drug needs to interact with.
Oh, okay. So finding those targets is like the first step to developing a new drug.
Exactly. And QML can help us sift through all that data and find the best targets.
It's like having a quantum detective.
Precisely. And QML could even help us optimize the properties of drugs that are already on the market.
Optimized.
Yeah, like we could use QML to tweak the structure of a drug molecule to make it absorb better or maybe reduce the side effects.
Okay. So we're using quantum computing to make drugs better.
Essentially.
Yes. That's pretty amazing.
Yeah.
It seems like QML could really revolutionize drug discovery and lead to like a whole new era of personalized medicine.
It's definitely a very exciting possibility.
It is. But QML's impact goes beyond medicine. It could also have a huge impact on material science, right?
It could. Material science is all about designing new materials with specific properties.
Right.
Everything from the materials we use to build airplanes to the semiconductors in our computers, and QML could completely revolutionize how we design these materials.
Okay, so how does QML actually apply to material science?
Well, one of the challenges is to predict the properties of a material based on its atomic structure. Simulating all those interactions between electrons and atoms.
Oh, right. And those interactions are governed by, quantum mechanics. So classical computers have a hard time with that,
I
right?
do.
But quantum computers don't.
They don't. They can simulate those interactions much more accurately.
So instead of relying on, trial and error in the lab, we could use quantum computers to design those materials from scratch.
Exactly. And we could predict their properties before we even make them.
That's incredible. Like we could design materials that are super strong but incredibly lightweight,
Right.
or materials that can conduct electricity perfectly.
Right. It's a really exciting field.
It is.
Yeah.
And it sounds like it's already starting to happen.
It is. Researchers are already using QML to design new catalysts for fuel cells, for example.
Wow.
And even creating new materials with properties that we haven't even imagined yet.
That's mind-blowing. Okay, so we've talked about medicine and materials. What other areas are you particularly excited about?
Well, I think the application of QML to financial modeling is incredibly interesting.
Financial modeling.
Yeah.
Like predicting the stock market and stuff like that.
Exactly. Predicting market trends, assessing risks, making smart investment decisions.
Okay, so how could QML help with that?
Well, QML algorithms could potentially speed up those calculations, improve those risk assessments, and even uncover patterns in market data that we might not be able to see otherwise.
So we could make better investment decisions, manage our money better, maybe even predict, when the market's going to crash.
Well, I don't know about predicting market crashes with complete certainty. That's still pretty challenging.
Okay.
But QML could definitely help us understand the forces that drive those markets.
That's still incredibly valuable.
Mm.
What are some of the specific tasks in financial modeling that are good candidates for QML?
Well, one is portfolio optimization.
Portfolio optimization.
Choosing the right mix of assets to invest in to balance risk and return.
Okay.
It's a complex task, but QML could make it a lot more efficient.
So instead of relying on, traditional financial models or even just like gut feelings,
Yeah.
we could use quantum computers to create optimal investment strategies.
Exactly. And QML could also be used to improve risk management, identifying and mitigating those financial risks.
Right, because there's always risk in the market.
Always. And financial institutions face a whole range of risks, from market volatility to credit defaults.
Yeah.
And QML could help us model those risks more accurately and develop more effective ways to manage them.
So we could use quantum computers to make the financial system safer and more stable.
That's the hope.
That's amazing. But QML isn't just about making money.
It's not. It can also be used to address those broader societal challenges.
Like what?
Well, we could use it to develop more accurate and fair credit scoring systems, for example.
Okay.
Or even to optimize the allocation of resources in social programs.
So it's not just about making the financial markets more efficient. It's about making them more fair and just as well.
Exactly. QML could really be a tool for social good.
This is incredible. Feels like QML has the potential to impact almost every aspect of our lives.
It does. It's a very powerful technology.
Well, before we get totally lost in the possibilities, let's take a minute to reflect on everything we've discussed so far.
Okay.
We started by talking about the basics of machine learning, both the traditional and the quantum approaches.
Right.
And then we explored that incredible world of quantum mechanics with all its strange and counterintuitive concepts.
Superposition, entanglement, quantum parallelism.
Yeah, all that good stuff.
Yeah.
And then we saw how we can use those concepts to create those powerful new algorithms for machine learning. And then we looked at how QML could be applied to all sorts of fields.
Drug discovery, materials science, financial modeling, even social good.
It's clear that QML has this enormous potential, but it's also facing some pretty big
It
challenges.
is. We need better quantum computers, more efficient algorithms, and we need to figure out how to integrate quantum computing with our existing systems.
Right.
It's a complex undertaking.
But the potential payoff seems worth all the effort.
It does. It's a very exciting time to be working in this field.
Absolutely. So before we get totally lost in all the possibilities of the future, let's bring things back down to earth for a minute. You mentioned earlier that QML could have a big impact on drug discovery. Can you elaborate on that a little bit? Like, how are these algorithms actually being used in that field?
Well, one of the key challenges in drug discovery is understanding how molecules interact with each other.
Okay.
And those interactions, well, they're governed by quantum mechanics, which makes them super complex to simulate on a classical computer. But quantum computers, well, they're naturally suited for that task.
Right, because they're quantum themselves.
Exactly. So we can actually use quantum computers to simulate those molecular interactions in a way that's much more accurate and efficient than we could ever do on a classical computer.
That's incredible. So we can use quantum computers to design drugs at the atomic level.
You could say that. We can use them to simulate how a drug molecule might interact with a protein in the body, for example, and that could help us to predict whether a drug is going to be effective or not.
That's amazing. So it's like having a virtual lab where you can test out all these different drug candidates before you actually have to make them in a real lab.
Exactly. It could really accelerate the drug discovery process.
That's revolutionary. What other applications of QML are you excited about in drug discovery?
Well, QML could also help us analyze those massive data sets of biological and chemical information that we have available to us.
Great, because there's just so much data in biology and chemistry. It's almost overwhelming.
There is, and QML could help us to sift through all that data and identify those promising drug targets.
Your targets.
Those are the specific molecules in the body that a drug is designed to interact with.
Oh, okay. So finding those targets is like the first step to developing an effective new drug.
It is, and QML could help us to do that much more efficiently and accurately.
It's like having a quantum-powered detective, that can just sift through all that data and find the clues that we need.
Exactly. And QML could even be used to optimize the properties of drugs that are already on the market.
Optimize? Like, what do you mean?
Well, we could use QML to tweak the structure of a drug molecule, to make it absorb better, maybe reduce the side effects, or even help it cross the blood-brain barrier more effectively.
So we're basically using quantum computing to make those drugs better.
That's the idea.
That's amazing. It seems like QML could really revolutionize the whole field of drug discovery.
Right.
And lead to, more personalized medicine, more targeted therapies, and just better treatments overall.
It's a really exciting prospect.
It is. But QML's impact isn't just limited to medicine, right? I mean, it could also have a huge impact on material science.
It could. Material science is all about understanding and designing new materials, with specific properties.
Right.
And QML could completely change the way we approach that.
Okay. So how would that work? How does QML actually apply to material science?
One of the key challenges in material science is to predict the properties of a material based on its atomic structure. And that involves simulating the interactions between all the electrons and atoms in that material.
Okay. And those interactions are, they're governed by quantum mechanics,
Yeah.
which means that classical computers have a hard time with that, right?
Exactly.
But quantum computers, they don't.
They don't.
They can handle that.
They're naturally suited for simulating those quantum interactions.
So instead of having to rely on, trial and error and experimentation in the lab, we could actually use quantum computers to design materials from scratch and predict their properties before we even make them.
Exactly.
That's incredible. We could design materials that are super strong but incredibly lightweight, or materials that can conduct electricity perfectly with no resistance.
That's right. It's a really exciting field with a lot of potential.
It is, and it sounds like it's It's already starting to happen.
It is. There are researchers already using QML to design new catalysts for fuel cells, for example,
Wow, that's amazing.
and even creating new materials with properties that we haven't even imagined yet.
That's incredible. So, okay, we've talked about medicine and materials. What other areas are you particularly excited about?
Well, one that I find particularly intriguing is the application of QML to financial modeling.
Financial model.
You know, predicting market trends, assessing risks, and making investment
Oh,
decisions.
right. That's a field that relies on a ton of data and really complex algorithms.
Exactly. And QML could revolutionize the way we do all of that,
Right.
by speeding up calculations, improving those risk assessments, and potentially even uncovering patterns in market data that we might not be able to see with traditional methods.
So we could make better investment decisions. We could manage our money more effectively, and maybe even predict when the market's going to crash.
Well, predicting market crashes with complete certainty is probably still a long way off, even with the power of quantum computers.
Okay.
But QML could definitely help us to understand the factors that influence those financial markets much better than we do today.
That's still incredibly valuable.
Yeah.
What are some of the specific tasks in financial modeling that are good candidates for QML?
One is portfolio optimization.
Portfolio optimization.
Yeah, it's the process of choosing the right mix of assets to invest in to balance risk and return.
Yeah.
It's a computationally very challenging task, but QML could potentially do it much more efficiently than classical algorithms.
So instead of relying on those traditional financial models or even just gut feelings,
Mm.
we could use quantum computers to create those really optimal investment strategies.
Exactly. And QML could also be used to improve risk management, identifying and mitigating those potential financial risks.
Right, because there's always risk in the markets.
Always.
Yeah.
Financial institutions, they face all sorts of risks, from market fluctuations
Yeah.
to credit defaults and operational errors, you name it.
Yeah.
And QML could help us model those risks more accurately and come up with better strategies to manage them.
So we could use quantum computers to make the whole financial system like safer and more stable.
That's the hope, yes.
That's amazing. But QML, it's not just about, making money, right?
Right.
It could also be used to address those broader societal challenges that we're facing.
Exactly. Things like poverty and inequality.
Really?
Well, for example, we could use QML to develop credit scoring models that are more accurate and fairer,
Right.
or even to optimize the way we allocate resources in social programs.
So it's not just about making the financial markets more efficient, but it's also about making them more just and equitable.
Exactly. QML could be a really powerful tool for social good.
This is incredible. It seems like QML has the potential to really impact almost every aspect of our lives.
It does. It's a really powerful technology.
Okay, well before we get totally lost in all the possibilities of the future, let's make a minute and just kind of reflect on what we've discussed today.
Sure.
We started by talking about, just the basic ideas of machine learning, both the traditional approach and then the quantum approach.
Right.
And we explored that really mind-boggling world of quantum mechanics.
Superposition, entanglement, quantum parallelism, all those fun things.
All that good stuff. And we saw how we can actually use those concepts to create these really powerful new algorithms for machine learning. And then we talk about how QML could potentially be applied to all sorts of different fields.
Yeah, drug discovery, material science, financial modeling, even social good.
Right, and it's clear that QML has this enormous potential, but it's also facing some pretty big challenges too.
It is. We need better quantum computers, more efficient algorithms, and we need to figure out how to integrate quantum computing with our existing classical systems.
Right.
It's a very complex undertaking.
But the potential payoff seems worth all the effort.
It does. It's a very exciting time to be working in this field.
Absolutely. So what's next for QML? What are the big questions that researchers are trying to answer right now?
Well, one of the most important areas of research is developing those more efficient and robust quantum algorithms. The ones that can handle the messy realities of real world data.
Right, because it's one thing to come up with these really clever algorithms in theory, but it's another thing to actually make them, work on real data.
Exactly. We need algorithms that are both powerful and practical, that can deliver real benefits in those real world applications.
Makes sense. What other areas are you personally excited about?
Well, the exploration of new quantum hardware platforms and architectures is incredibly exciting. We're always looking for new ways to build quantum computers that are more powerful and more stable and more scalable.
So it's like a quest for the holy grail of quantum computing, a machine that can really unlock the full potential of QML.
You could say that, yes. And
Yeah.
it's not just about building those bigger and better quantum computers. It's also about exploring completely new types of qubits, new quantum computing architectures,
Yeah.
each with their own unique advantages and challenges.
It's like we're in the early days of aviation, just trying out all these different designs and materials to see what works.
I like that analogy. And
Yeah.
and just like those early pioneers of flight, we're constantly pushing the boundaries of what's possible, driven by this shared vision of a future where quantum computers can solve problems that are just completely intractable for classical computers today.
Absolutely. And speaking of pushing boundaries, what about the whole challenge of integrating those quantum computers with our existing computing infrastructure? It seems like that's a pretty big hurdle to overcome.
It is. We need to figure out how to connect those quantum devices to our data centers, to our existing workflows in a way that's seamless and efficient.
So we're talking about building those bridges between the quantum world and the classical world.
Right, and creating this hybrid computing ecosystem where each type of computer can really play to its strengths.
Yeah. That makes a lot of sense. And beyond those practical challenges, what about the theoretical foundations of QML? Are there still some big questions that we're grappling with?
Absolutely. We're still just beginning to understand why and how these quantum algorithms work so well. We need to develop a much deeper understanding of the interplay between quantum information theory and machine learning to really unlock the full potential of QML.
So it's not just about building and testing algorithms. It's also about, really delving into the theory behind them and trying to figure out what's really going on.
Exactly. That kind of fundamental understanding is what's going to lead us to those truly transformative breakthroughs.
This is all so fascinating. It seems like QML as a field is just constantly pushing the boundaries of our understanding, not just of computing and machine learning, but of the very nature of information and knowledge itself.
I agree. It's a very interdisciplinary field.
Yeah.
It brings together physicists, computer scientists, mathematicians, and researchers from many other fields.
And it's a field that's just full of potential, not just for technological advancement, but for really tackling some of those big challenges that we're facing as a society.
Absolutely. We've already talked about the potential of QML to revolutionize fields like drug discovery and materials science, but its impact could go far beyond that.
What other big problems could QML help us to solve?
Well, for example, QML could potentially be used to help us address climate change.
Really, climate change.
Yes, we could use quantum computers to simulate the complex processes that govern our climate,
Okay.
and that could lead to more accurate predictions and more effective strategies for mitigating climate change.
So we could use quantum computers to basically model the planet
In a way, yes.
and then figure out how to make it healthier.
Exactly. And QML could also be used to accelerate the development of renewable energy technologies like more efficient solar cells or more powerful batteries.
So we could use quantum computing to create a more sustainable future for everyone.
Precisely. And those are just a couple of examples. The potential applications of QML for addressing those societal challenges are vast, and we're really only just beginning to explore them.
This is so inspiring. It feels like we're on the cusp of this whole new era of scientific discovery and technological innovation.
It does feel that way, yeah.
One that could really change the way we live and work and interact with the world around us.
I agree. It's a very exciting time.
Well, on that note of optimism and anticipation, I think it's time to wrap up our deep dive into the world of quantum machine learning. We've covered a lot of ground today, from the fundamental concepts to the mind-blowing possibilities.
It has been a fascinating discussion, and I hope our listeners have enjoyed exploring this exciting and rapidly evolving field with us.
I'm sure they have. And if you're interested in learning more, be sure to check out those resources that we've linked in the show notes. There's a whole universe of information out there just waiting to be explored.
And as always, keep those curious minds engaged, never stop learning, and keep pushing the boundaries of knowledge.
Absolutely. Thanks for joining us on the deep dive. Until next time, keep exploring the wonders of science and technology.